everyone. Today I wanted to continue our discussion about CRCs and then move on to something called ARQ. Okay, so CRC is the cyclic redundancy check, and we saw how to choose this divisor polynomial so that we'd be able to detect single bit errors two-bit errors, odd number of errors. Okay, we looked at those three. And there was one more point which I hadn't mentioned last time, which was how to detect a burst of errors. So here let's say that this is the data. Let's say this is the code word, which is data and the CRC concatenated. So sometimes this is used as a notation for concatenation of bits. So these are the bits 1 0 1 0 0 0 1 0 0. And there may be a burst of errors due to some reason. Let's say there's a temporary disturbance on a wire due to some reason, because of which let's say few of these were in error. Let's say these bits. Okay, so there are 7 bits. So suppose only these 7 bits were in error. There was a burst of errors. Okay, and all these bits got flipped due to some reason. So what would the error bit string look like? So you would have this bit string, so we would write this as E of x and how would we write this? Well, it's really going to be a polynomial of this form. It's going to be something like this. Let's say that the first position was at okay, so this is the 0th position, so let's say that this was at position I plus 1, or this was at position I if we are counting from 0. So ith position from the end here, this is, let's say, the 0th position. And the burst was of, let's say, length L. So what would this look like? Well, of course, we'd have x to the power of I corresponding to this bit, plus x to the power of I plus 1 and so on. And there are L bits here, so we're going to end up with x to the power of I plus L minus 1. Okay, so this is my error vector and the error polynomial, I should say. And the question is whether the CRC divisor is going to be able to detect this sort of an error. So let's assume that the CRC polynomial looks something like this: x to the power of k plus 1, or it's of this form, and we can have anything here. Okay, so this is the polynomial of which we are going to use to do the mathematics for computing the CRC. So the question is, we know that code word itself is going to be divisible by C of x. That's the way that we have created this code word. And the question is E of x divisible by C of x? So let's rewrite this polynomial in terms of x to the power of I multiplied by x to the power of L minus 1 plus x to the power of L minus 2 and so on plus 1. So let's write E of x divided by C of x. And this divided by x to the power of k plus, we're saying we can have anything in between, plus 1. So is E of x going to be divisible by C of x? Okay. Now clearly you can never pull out a factor of x from all of this because you have 1 here at the end. So there is no factor of x over here. So let's just write that out here. There is no factor x to the power of p for any p which can be pulled out of this. So we don't have to worry about this x to the power of I term. Nothing is going to cancel over here. So if at all C of x has to divide E of x, it would have to divide this quantity over here. So is this quantity divisible by C of x? And so clearly if L minus 1 is less than k, then C of x cannot divide this particular polynomial. Okay, because it's a polynomial smaller than this one. So if you want a rigorous proof, of course, because these polynomials are a little bit tricky. They are not exactly corresponding to binary numbers because we have this addition which is XOR and so on. But you'll have to think. So suppose we had x to the power of k plus so on up to plus 1. And we'd have to be able to multiply it by something else to get this polynomial. And the question is, can such a thing exist? Okay, and obviously you can't have it because whatever you have here, whatever is the resultant, will have power of k or greater. Okay, so this product is going to have x power of k or higher than x to the power of k, right? And on this side you have less than k, so it's not going to be possible. Okay. So what does this mean? So what we have shown is that if you have a device of polynomial of this kind, x to the power of k plus and so on plus 1 at the end, that this we have to understand that this is something we have assumed, that we start with x power of k and we end up with 1. Then any burst of errors of length k such that L is less than k plus 1 will be detected. So that's a good property. So suppose the CRC 16 we were using, for example, and we had k was 16. That means bursts of length less than 17, that means bursts of length up to 16 will be detected by that CRC. Okay, so that's a good property to have, so that we can also deal with bursts of errors. Okay, so single bit, 2-bit errors, odd number of errors, and also a burst of errors is something that we can catch. So a good CRC designed well will be able to do all of these. Okay, so can we detect all possible errors? No, because you can always go from one valid code word to another valid code word, and then there's no way we're going to be able to tell that an error has occurred. Okay. So this is what I wanted to talk about CRCs. And of course there are a few other topics we need to cover in data link layer, and one of them is called ARQ, which stands for automatic repeat request. So the acronym is formed from these letters. And this ARQ deals with reliability. So we said that we have 5 layers. This is the convention we are following in this class, and of course people might add more layers or remove some layers depending on which textbook you look at. So we said that one of the transport protocols, which is called TCP, handles reliability, but the DLL also handles reliability. So why would we want to have reliability at the DLL? Because sometimes the channel itself, the you can say the link between two consecutive nodes on the path may not be very reliable. So TCP is a little bit inefficient in taking care of reliability because it takes it some time to figure out whether a packet has been lost or not. So of course the term to use in TCP is segment. We mentioned this in an earlier class. So essentially a message is called a segment in TCP. At the network layer you call it packet, at DLL you call it a frame. So if a segment is lost, TCP tries to figure that out and retransmits it, but that takes a lot of time, so it's inefficient. So if you have a link which is, let's say, very noisy or prone to errors, it makes sense at the data link layer itself to retransmit the message. Okay, and in fact Wi-Fi uses ARQ. Let me just write that down. And since the wireless link for Wi-Fi is prone to so many errors, it makes sense to actually retransmit the packet there if at all it's detected as being lost. Or I should say not packet, I should say frame. So how is this going to work? And most of the concepts in networking, or in fact any systems course, will be very intuitive. So if you try to think of the solution on your own, you'll probably come up with the same one. Okay. So what do we do? So let's say this is the sender, and this is the receiver of the frame. And I'm going to draw like this vertically a time axis. So time progresses this way. And let's say that the sender sends out a frame. And I'm drawing it in a slightly exaggerated fashion. So this is when it actually sends out the frame and it propagates over space and reaches the receiver at some particular point in time. Okay, so this is when the first bit is sent out, and this is when the last bit is sent out. So because no information travels instantaneously, it travels at the speed of light. Any sort of wireless signal or even an electrical signal on a wire will take some time to reach the other end. Even an optical signal, it would travel at the speed of light. Yeah. So there may be some quantum computation which is instantaneous, right? You guys may be familiar with those sorts of ideas. But in practical situations, we are using electrical signals or optical signals which travel at the speed of light. Okay, so I'm sending out, let's say, but this is T1, let's say, or this is T0, this is T1. I'm sending out the frame, I'm sending out the signal which corresponds to this frame over this period of time. And the frame travels and it reaches the receiver a little bit later. So, suppose I were to, right, so this is the speed of light delay. Okay, so the frame goes across, and the question is, how does the sender know whether it's reached there reliably or not? So think about it. Suppose you were designing the system, you sent out a frame. How do you know the other side has got it or not? And we'll see in the wired Ethernet, in a sort of a bus like LAN situation, we look at a little bit later. You can actually, from the physical layer information, you can find out whether the frame has reached the other end or not. But suppose you don't have any information from the physical layer, right? We are dealing at the DLL layer. So I just care about bits. I've sent out a set of bits and I want to know whether the other end has received it or not. So what do I do? So the obvious thing to do is that you ask the other end to send a reply, what is called an acknowledgement. So this is your data frame. Which would contain actually higher layer bits and so on with a CRC and whatever. And here you have an acknowledgement. So if the sender gets back an acknowledgement, he knows that the frame has reached the other end. So that's the basic idea. So so obviously the question which comes into mind is, how long should I wait for this acknowledgement? Right? And really it depends on how long does it take the frame to reach the other end. It's not instantaneous, neither of these is instantaneous. So let's think about that. How long to wait for an ACK? And okay, and you might think, how big is this ACK frame? Okay, so notice that I've drawn them a little bit differently. So this is a bit wider than this one. Okay, so an acknowledgement usually would just say, this is the frame I'm acknowledging, and so it doesn't require a large number of bits. Whereas this data frame could be quite long, maybe few kilobytes even. Typically an Ethernet frame would be around 1500 bytes, the large size frame. Okay? So this could be much larger, and typically this would be small. So the question is, how long should the sender wait for the frame? Because essentially what ARQ is going to do is, it's going to make the sender wait for a certain amount of time, and if it doesn't see an acknowledgement in that much time, it retransmits the frame. So that's what ARQ is about. I transmit a frame, I wait for some time. If I get the acknowledgement, I'm done. I don't have to worry at all. But if no acknowledgement comes, then I retransmit. So I have to wait for some time. This we have to set accordingly. When we study TCP, we'll realize that this is a non-trivial question, setting the timeout value. Because what is the destination? The destination could be google.com, it could be IIT's website, right? And IIT's website, obviously, if you're on campus, is going to take, the round trip time is going to be very, very low. Whereas if you're sending it to Google, it may take maybe 10 times more even, for a message to reach there and to get an acknowledgement. So TCP is dealing with end-to-end round trip times, which is a very tricky issue. But luckily in the link layer, we are only dealing with a single link. Okay, so it's a single DLL link. So the message goes here and comes back. And what we need to do is we need to figure out what is the round trip time. So the round trip time is, so let's say I start my timer over here, and let's say I measure the time till the last bit of the acknowledgement comes, and let me say that this is the round trip time. So in a Wi-Fi system, you might think, what should the standard set this round trip time to be? And Wi-Fi systems, let's say you have an access point, and you have your mobile or your laptop and so on. And so Wi-Fi systems are designed that this distance is of the order of hardly 10 meters. Okay, 10 meters or maybe a little bit longer, tens of meters, a few tens of meters. Okay, that's what you design the system for. So in this sort of a situation, you know what is going to be the round trip time. How long is your signal going to take to reach here? Okay, and how long is this frame going to take to reach the other end? Okay, and how long is it going to take to come back? Okay, so all of these, the speed of light is coming, let's say at least twice. You have the speed of light delay coming in. Plus there is some processing delay. I mean, it takes some time from when the first bit reaches the other end to the last bit of the frame reaching the other end. Okay. And that of course depends on your modulation rate and so on. If you're using a higher modulation rate, this time is going to be smaller. But if you're using BPSK, then maybe it's going to be longer. Okay. And of course we have to take the time for transmission of this ACK and so on. So the standards bodies will figure out that in the worst case, let's say that you have few tens of meters, and it may take several nanoseconds at least to go across. Okay, so speed of light is what? 3 times 10 to the power of 8 meters per second. Okay. And nanoseconds of course is small if you think about it, but with our electronic systems, our computers, we actually operate at those time speeds. Our clock cycles are of the order of nanoseconds. Right? A gigahertz clock is 1 nanosecond. Okay. So these times are non-trivial for us, I mean, because actually our communication systems are operating at with very high speed clocks also. Okay. So you would figure out what this round trip time is going to be typically, given the size of a wireless frame that you send out. How long is this going to take? Suppose you're using BPSK in the worst case, and suppose the distance is the maximum that you're designing for. So you have some idea what the round trip time is going to be, and you will set your timer accordingly. So you won't set it exactly equal to the round trip time, because that may be cutting it too fine. Maybe you will have it 2-3 times the round trip time to be on the safe side. So what are we going to do? So this is when everything works fine. What if I don't, let's say the frame is corrupted, the CRC detects it, and so the receiver discards the frame. Okay, that's one thing that could happen. Another thing that might happen is that the receiver got the frame and sent the acknowledgement, but for some reason the acknowledgement didn't reach the other end. Okay, so what does that mean? I mean, so suppose it sent out some bits, maybe some bits of the ACK frame were themselves in error. So the sender had no idea what was coming. The CRC of this ACK frame didn't match, so it just discarded the frame. Okay, that's possible. And in the wireless frame, if there is so much of noise, maybe it couldn't detect any bit at all. That too may be possible. Okay, maybe there was somebody else transmitting a Wi-Fi signal, let's say, and this was acknowledgement was simply not audible to the sender. So all of these things could happen. Okay. Let's see what happens when a packet is actually, or a frame is in fact lost in the data link layer. Okay, so we're assuming that the data link layer uses ARQ. So this is at the sender and this is the receiver. So we send out a frame, and just for convenience I'm not drawing this frame as existing for some amount of time, but that's understood. So I'm sending a frame, let's call it frame 1, and what I should normally get back is an acknowledgement. Let's call it A1. So now the timeout should be set to be larger than the round trip time. So since this particular acknowledgement has come back before the timeout, we get rid of the timeout for this particular frame. Okay. And what we could do, so let's just call this timeout T1 corresponding to this frame. What the sender could do is he could send another frame after this. So what we do is we disable T1 here. And let's say that we send another frame 2. But due to some reason, let's say this frame could not reach the other end. So let's say the frame got lost or got corrupted. So it didn't reach this particular end. Maybe some bits were received in error, so no acknowledgement was sent. So what's going to happen now? So we have started a new timer here, T2. Which is of, let's say, a fixed duration given by the protocol. So the sender is going to keep waiting until this timer expires. And what it could do is it could resend the frame. And let's say that this time the frame gets through and the acknowledgement was sent. Okay. So this time again we are going to set a timer. So let's call this T2 0 just to say that it was the first time for this particular frame. Now for the same frame I am setting another timer, okay, for the second attempt at sending that frame. And let's say that the acknowledgement now got lost for some reason. It didn't reach here. So the frame got through correctly, but the acknowledgement didn't reach the sender. So actually there is no need for the sender to send another frame, another copy of this frame 2. But the problem is it doesn't know what has happened. It didn't get back the acknowledgement. So it's going to assume the worst case. And when this timer expires, it can send the frame again. Let's say that this third time we got lucky and the acknowledgement reached. the sender. Okay, so this third time he sent out the frame, again he had to set a timer. Let's call it T2 2, corresponding to the third time he sent. But since the acknowledgement came here, he can disable this timer. Okay, so this is ARQ in its most basic implementation, where you wait for a particular timeout after sending a frame. If you haven't got back an acknowledgement, then you retransmit the frame, and you keep repeating that till you get back an acknowledgement. So we saw that there could be cases where you resend a frame unnecessarily, even though it reached the other end, because you didn't get back an acknowledgement. You might send it again. There also could be cases where you unnecessarily send a frame just because you set the timer improperly. So let's look at that case. So the sender and the receiver. So let's say he sends out frame 1. And the acknowledgement, let's say, comes back, everything is fine. But the timer value was set to be too small. So what he does is he sets the timer, let's call it T10, to be very small. Okay, let's just extend it a little bit. So here the timer expires. And now what the sender is going to do is he's going to retransmit. He thinks that my timer has expired, the frame hasn't reached because I didn't get an acknowledgement. So he resends the frame again. And the receiver doesn't know what's happening, right? So it's possible that the acknowledgement got lost the first time. So even though he's getting the frame a second time, he will send back an acknowledgement. Okay, so every time a frame is received here, the receiver should send back an acknowledgement, even if he has received the same frame earlier, because it's possible that the acknowledgements were lost, and which is why the sender is continuously sending the frame. Okay. So this is what happens, and of course the timer is set again over here. So for this particular frame, the timer is set again. Now what happens? So he sent the frame a second time and he got back an acknowledgement before this timer expired. And so he might think that this acknowledgement is for the second attempt of his. Okay, so what he's going to do is at this point, he's going to disable the timer. And he might send another frame F2 or something like that. So in this particular case, everything went off correctly, but the timer value was set too small, because of which unnecessarily 2 frames were sent, 2 copies of the same frame, and 2 acknowledgements were received back. So this tells us that we need to set this timer properly. It shouldn't be too small. If it's too large, that's fine. You're not going to send unnecessarily the same frame again and again. But there's another problem there, that you'd be wasting a lot of time in certain cases when the timer value is quite large. So let's say that a particular frame is sent out here and the timer value is set to be extremely large. Let's say something like this. Now let's say due to some reason the frame is lost. So the sender just keeps waiting. Suppose he had, this is the expected time to get the acknowledgement, let's say. Of course, in this case, the acknowledgement wasn't sent. So he could have set the timer smaller, but it's set very large now. So he will retransmit the frame here. So there's a lot of time wasted. Okay, and he could have been more efficient in using the channel by sending out the frame earlier. So the timer shouldn't be too large either. Okay, so the protocol should define it, and for something like Wi-Fi, you know what the round trip times are going to be because you know how far in space your let's say your laptop or mobile is going to be from the access point. Okay, but generally if you have wireless systems where the receiver is very far from the sender, or the further away it is from the sender, you will have to set this timer higher in order to take into account the fact that the round trip time will also be high. Okay. So the timer value has to take into account the speed of light delay from one end to the other and back, so at least 2 times the speed of light. But it also needs to take into account the time for which this particular frame is sent out over the air, and also it needs to take into account the time for processing this frame at the other end and so on. Okay, so all of these things have to be taken into account while setting the timer appropriately. So when we talk about medium access protocols, which we look at from the next lecture onwards, we will see that not always are these timer values going to be the same for the same frame. What we'll see some of the protocols doing is that they will actually exponentially increase these timer values for successive transmissions of the same frame, and we'll see why that it is, why they do that. Okay. So this is essentially how ARQ works, and let's talk a little bit about state diagrams. So ARQ is the first protocol we are looking at in some detail between more than one entity. Right? So you have source, sender and receiver interacting in some way. Okay? So the physical layer algorithms that we looked at for detection and so on, the receiver was operating on its own. It wasn't waiting for some message to go back to the sender and the sender send something back. Okay? So essentially when you talk about protocols and you design protocols, we represent them in the form of state diagrams and flowcharts. So let's look at what a state diagram would look like. So you would represent it as a set of states, and let's just take this example of a protocol which has 3 states. And within a state, we are waiting for something to happen. So we are waiting for an event to occur. And when that event occurred, we will typically jump to another state. So let's say that we are in state 1 and some event took place. Let's say event A. What we will do is we will take some action. Okay, so something happened. One example could be that the timer expired, right? That would be an event, and then we take an action. It could be resending the frame again. And let's say if event B occurred rather than event A, we might jump to state 2 instead. Maybe event B could be acknowledgement was received, right, before the timer expired, and then we jump to state 2. Right? And similarly, we might jump from state 2 to state 3 if some other event took place. So this state diagram that we are drawing is for one of the nodes. Like for example, for the sender, we will have one state diagram. Okay. And if we also want to draw it for the receiver, we would have another state diagram expressing which states the receiver are in. Okay. So it could happen that when you have a particular event, you stay in the same state. So let's say that event D took place when we were in state 3, and we took action D and we jump back to the same state. Okay. So this is how we would draw a state diagram, and for the event and action we will typically draw a flow chart, so to represent what happens. So we will express all the actions to be taken, or the steps of the action. So there will be whatever, a typical flow chart which says what is done. Maybe there's an if sort of an if statement over here in the algorithm that we're running to take this action, right? And so on, right? So when you come up with a protocol, normally you would draw a state diagram, and also you would draw flow charts for each of the actions. So what is the state diagram for, let's say, this ARQ protocol? Let's say the state diagram at the sender for ARQ. So let's say the data link layer is running ARQ. Okay, so let's say that initially it is idle because there is no information which has come from a higher layer. So we are waiting for message from the higher layer. And let's say we got a message from a higher layer, so then we move to another state. Say we got message from higher layer. So what do? Well, we send a frame. Containing that message. And we set our timer. So now we've jumped to the sent state. So let's say sent frame. Now what can happen? Let's say that we got an acknowledgement for the frame. So what do we do? That is the event that occurred. So what we are doing is that we are going to write it in this particular notation where we have event slash action. So got an acknowledgement, we stop the timer, and in addition we dequeue the packet or dequeue the message because it has been received by the other side. So what do I mean by dequeue? So we have the various layers. We have application layer, transport layer, network layer. So each of these is let's say a software module, and the message is being sent from one module to the other. So we are talking about the physical layer. So let's say the network layer is sending messages. It could be sending faster messages at a faster rate than the DLL can handle. So the DLL has a queue over here. Whenever you have data coming in faster than you can process, you would want to have some buffer in which to store it, right? And we represent that as a queue. So these are, let's say, messages coming in which are stored, and so we are using ARQ to send this one. So we sent it out and we got an acknowledgement, and after that we should remove this from the queue. So remove from queue, which I call DQ. After the ACK was received. Okay, so this is if everything went off correctly, but what if the timer expired before I got an acknowledgement? So let me write that here, that timeout occurred. And what do we do when this particular event occurs? We will resend the packet or resend the frame and set the timer again. And we go back to the send frame state because again we are waiting for the acknowledgement. Okay, so this is what the protocol would look like, the state diagram at the sender. And you can, as an exercise, draw the state diagram for the receiver. What would it look like? Okay, so let's say that it's idle, and what happens, right? If it gets a message, what does it do? Right, and I mean you'll be able to draw a simple state diagram in that particular case. Okay. So this is all about ARQ, and ARQ is used like by protocols such as Wi-Fi. Okay, lots of wireless protocols tend to use ARQ, and but of course there are many other things in these wireless protocols at the data link layer, and we'll talk about some of them from the next lecture on.